Good morning students, welcome back. We will discuss about the remaining part of the optics in this video. Let us continue with the topic of refraction of a light due to prism. As you can see on the screen, the figure shows the prism and a ray of light is incident on that. Consider that as point where light is incident, as you can see on the screen. Now, a cross section perpendicular to the prism made a transparent medium as shown in the figure. A ray of monochromatic light is incident on point. Because of that surface, it gets refracted from one surface of the prism, and according to Snell's law, it is refracted and travels the other path but somewhat deviated. This experienced deviation point or the ray incident on the surface at other point will travel to a other surface, and again it shows a deviation, as you can see on the screen. The angle between the incident ray and the emergent ray is called angle of deviation. To know the extent by which the incident ray is deviated, let us obtain the relation between the angle of prism A and the angle of incident I and the angle of emergence E and the angle of deviation delta. All these three angles or four angles you can see clearly on the screen. A delta, angle of deviation, E, angle of emergence, I, angle of incident, R, angle of refraction. So that's what we are going to find here, or we will dealing with in this video. We know that from the figure or from the using the maths law, you can say that your A plus O is 180 in a quadrilateral A, P, Q, O. But if you consider it as triangle O, P, Q, you can say that R1 plus R2 plus O is your 180. Similarly, you can say or find for the two other triangle considered as DPQ from the figure DPQ. So here you can write as delta is equal to I minus R1 plus E minus R2 using a maths law. Remember, from 1 and 2 we know that A plus O is 180 and R1 plus R2 plus O is 180. You can write that A is equal to R1 plus R2. So using the equation 3, you can write your delta is equal to I plus E minus A, or other terms you can write in other way. You can write I plus E is equal to A plus delta. Thus, you can say that this equation gives the relation between the angle of deviation and angle of incident and angle of emergence and angle of prism. Now, it is clear from the equation that the angle of deviation depends on the angle of incident. From the sake of the simplicity, if you draw the graph of delta and I, it will show you a kind of parabolic slope. Just see in this manner. The angle of deviation with angle of incident. When angle of incident increases, the angle of deviation decreases. Particularly the value of angle incident and the angle of deviation comes minimum, that the angle is called the angle of deviation. At your delta I is equal to E and R1 is equal to R2 is equal to R same, after minimum deviation, the angle of deviation increases the angle of incident. So it is clear that angle of deviation depends on the angle of incident. You can think in that manner, both are not independent but dependent on each other. For example, refractive index of a material of a prism. Consider equation, your A is equal to R1 plus R2. Suppose your R1 and R2 are same, so you will write A is equal to R2. So your R will be A by 2. From the previous equation, I plus E is equal to A plus delta. You will get the equation 2I is equal to A plus delta. You can derive the equation that I is equal to A plus del divided by 2. According to the Snell's law, you know that mu is equal to sine I upon sine R. Now just apply this to terms of I and R in terms of the prism. You will get that your mu is equal to sine A plus del by 2 upon sine A by 2. But remember, in the prism, A can be considered as 60 when you are taking a perfect kind of prism or triangular prism. For the prism, the value of delta depends on the angle of prism, refractive index of material of prism and medium in which the prism is kept. We can calculate the refractive index of a material of a prism with the refraction of a medium in which it caps by measuring A and delta by using this equation. Now, refractive index by a small angle prism for a small angle incident. Generally, you know that it can be used by the equation or find by the equation mu is equal to sine I upon sine R. Here I is equal to your E and R is equal to R only, or R1 or R2, depends on your supposition. Suppose your I assumed to be a small, then R1 and R2 and E is also very small. So replacing the sign of the angle themselves, we get mu is equal to I upon R1 and mu is equal to E upon R2. Place this equation, I plus E is equal to mu, R1 plus R2 is equal to mu A, but you know that I plus E is equal to A plus delta. So you can write that your A plus delta is equal to mu A, or delta is equal to A plus mu minus B. Dispersion of the light due to prism. As shown in the figure, white light or the sun ray pass through the prism. The merged light is seen to disperse into various colors. Does the prism create the colors, or does the separate of the constituent colors of the white light? Newtonian arranged the two separate prism with angle of prism and same material, so that the result is different. But only if you take one prism, the result is different. So why it is happening? What is the reason? In physics, the term is known as dispersion. The phenomena in which the light gets divided into its constituent colors is known as dispersion of the light. A ray of white light first incident on the angle of prism, an emergent ray comes out from the other side of the prism, have different colors because of its frequency lambda wavelength difference, which can be understood by various means. The phenomena of splitting the ray of a white light into a constitute colors wavelength is called a dispersion of a light, or band of the colors of violet to red is called a spectrum. With the different 7 colors you can see on the screen, starting from violet to red, dependent upon its wavelength, cause the dispersion. You know that mu is equal to sin I upon sin R. Since here two different colors have different wavelengths, so it will have the different mu. So color are refracted at different angles and hence get the separated. Now just think, dispersion can be also explained on the basis of this equation. Equation says that mu is equal to A plus B upon lambda square plus C upon lambda C raised to 4, where A, B, C are the constant of the materials and lambda V is less than lambda R, mu is greater than mu R, but you know that A is equal to mu minus 1, therefore you can say that your delta V is greater than delta R, so color gets separated with the different angles of deviation. Violet is the most deviated and red is least deviated. Angular dispersion, the word dispersion and the word angular suggest you something. The difference in the deviation suffered by the two color in passing through prism gives the angular dispersion through a color. The angle between the emergent ray to the two color is called the angular dispersion between two colors. Those two colors, it can be red to red, red to blue, yellow to red, depends on what you are choosing. The rate of the change of angular of deviation with lambda phi is equal to T delta upon d lambda, which can be written as your phi is equal to delta difference. Now dispersion power. Dispersion power, it's also related with the rainbow. There is no reason to believe that you have not seen the rainbow in the rainy season. But do you remember that? Have you ever enjoyed the rainbow? Your back was facing the sun. You may ask, what was the sun to do with the rainbow? In fact, the sunlight is the reflected and the dispersed by the water droplets suspended in the atmosphere during the monsoon. This rainbow is a beautiful example of the dispersion of a light. However, internal reflection of a light, it is not necessary totally. Inside, the dispersion of a light also plays an important role for the formation of the rainbow. But other thing is important is dispersion power. The dispersion power of the material of the prism for the two colors is defined as the ratio of the angular dispersion for those two colors which you have considered. You may also define as dispersion per unit deviation. Omega is equal to phi upon delta, where delta is mean of deviation is the average. You can say delta 1 plus delta 2 divided by whole 2. Similarly for omega also you can write delta v minus delta r upon delta, or omega is equal to mu 1 minus mu 2 multiplied by a upon mu 3 minus 1 upon multiplied by a. The scattering of a light, blue color of the sky, and reddish color appearance of the sky at the sunrise and sunset. This is the example of that. Molecules of the atmosphere and other particles that are smaller than that longer wavelength of visible light are more effective in scattering the light of the shorter wavelength than the light of the longer wavelength. The amount of the scattered inverse proportionally to the 1/4 of the power of the wavelength. You will get a situation that a light from the sun near the horizon passes through the greater distance in the earth atmosphere does the light receive when the sun is overhead. Corresponding the greater scattering of the short wavelength accounts the reddish appearance of the sun at rising and setting. When you look at the sky in the direct way from the sun, you receive a scattered light sunlight in which the shorter wavelength is having a different phenomena and greater wavelength is having a different phenomena. Means you can say it's dealing in different ways. Thus this phenomena occurs of bluish and reddish observation. Now, before starting the compound microscope topic, let us just think that if a light is falling on the atmosphere, atoms and molecules as well as the small suspended particles like cloud particles, it is observed and immediately retarded in the different direction. This process is called a scattering of a light. As a result, a part of intensity of a light divides into a different direction having a different proportion. So what happens? If the size of a particle which scattered the light is smaller than the wavelength of the incident, the scattered particles are known as relay scattered. You can say that your I is directly proportional to 1 upon lambda raised to 4 or inversely proportional to 1 upon lambda raised to 4. Relay scattering of blue light is 8 to 9 times more than of relay scattering to the red light. Now, let us discuss something about the compound microscope. We have seen that a simple microscope magnifying power depends on D upon F. So, we are attempting to use a convex lens with a very small focal length. But here there is a practical difference. When F is very small, image is distorted. So practically F cannot be taken very small. And using the simple microscope, you can get the maximum magnification of 20x. There is a benefit of using a simple microscope that the image is magnified. Now, if you use the magnified image as the object for the another convex lens, you can further magnify it. With this idea, compound microscope is developed. You can see on the screen a basic diagram or figure for the compound microscope. Object AB is enlarged to A double dash B double dash. Where is our eye? The position, the lens function, the focusing, everything depends on here. The lens cap towards the object is called the objective, and the lens cap near the eye is known as eyepiece. The distance between the second focal point of the objective and the first focal point Q to the eyepiece is known as tube length L of the microscope. It is clear from the figure that the image obtained by the microscope is real, inverted and magnified, as you can see on the screen. See, here AB, so it's inverted, real and magnified. Moreover, this image acts as the object for the eyepiece, and eyepiece behave as microscope, giving a virtual magnified final image. The first image obtained near the focal point Q of the eyepiece, due to the final image is obtained at the considered as the large distance. Magnification obtained by compound microscope. Angular magnification or magnification power. Angular magnification or a magnification power of compound microscope is defined as the ratio of the angle beta subtended by the final image at the eyes to the angle alpha subtended by the object seen directly when object is placed at least some distance to the distance is visible. You can say that your m is equal to beta upon alpha, or in similar way you can write as m0 is equal to hi upon h0, that is your hi is equal to beta and h0 is equal to alpha. In other way you can also write your m0 is equal to L upon f0. These are the way to write the magnification equations. Now the image is obtained by the eyepiece at a very large distance. Its magnification can be obtained by equation m is equal to d upon f. D upon f, where f is equal to fe and fe is the focal point or focal length of a eyepiece. Using this two equation, you can write your m is equal to m 0 me. So your m will be equal to L upon f0 into d upon fe, will give you equation of magnification of compound microscope, which can be also derived in the various way. For example, see on the screen, your me is equal to 1 minus v upon fe, or me is equal to 1 plus d upon fe, and m0 is equal to v0 minus hu0. Sign is an important thing in this conversion. Since the object is placed close to the principal focus, the object and the image formed very close to the eyepiece, your u0 is equal to f0 and your v0 is equal to f. Thus you can write your m is equal to minus L upon f0 1 plus d upon fe, or by normal adjustment you can write your m is equal to minus L upon f0 multiplied by d upon fe. That's your magnification power for compound microscope. Now similarly, you have astronomical telescope. After observing minute from the astronomical telescope, you will see the vast difference in the image formed by this telescope and microscope. Minute object using the microscope, now it is a time to observe a very huge terrestrial object. There the minute objects are used, and here a bigger but at a very distance. A huge terrestrial bodies which are crores of kilometers away. Such bodies, in spite of being huge and very far from us, you can see a very small close to each other from our normal eye. But there is a difference when you see through a telescope. You can see on the diagram, two convex lenses are kept in such a way that the principal are coincide. The lens focusing of the object is called objective, and the lens near the eye is called eyepiece. Here the diameter of the focal length of objective are greater than the eyepiece. So here the eyepiece can be moved from to flow in the telescope tube. When the telescope is focused on the distance object parallel coming from the object real, inverted and small. On the second principal focus of the objective, the image formed on the eyepiece, this eyepiece is moved to the flow and get final and magnified image, inverted image, and the original object is certain distance. Angular magnification or magnification power of telescope, in case of that, you can define as the ratio of the angle beta suspended to the eyes by final image formed by the at least distance which is visible to the angle suspended at the eye object infinity when it's seen directly. Here also you can write this in similar way. M is equal to angle suspended by the final image to eye upon angle suspended by the object with the objective or eye, that is beta upon alpha. M is equal to beta upon alpha. K is equal to F0 upon Fe. This equation shows that to increase the magnification of the telescope, the focal length of the object should be increased, the focal length of eyepiece should be reduced. Your F0 plus Fe is an optical length of the telescope, so that the length of the type is L is greater than or equal to F0 plus Fe, and if your focal length of eyepiece is 1 centimeter, the focal length of your objective is 200 centimeter, the magnification of the telescope should be 200. Using this telescope, if the stars having an angular distance at 1 minute we observe should be such that 200 into 1 minute will give you 200 minutes, that is 33.3 degree angular distance from the each other, or can be existed as per your requirements. For the telescope, for the power and resolution, power to view two nearby objects are very important. The amount of light entering the object to the telescope is directly proportional to the square of the diameter of the object. Also, inversely, or you can say increase the diameter